Okay, so I want you to give me the range of this quadratic function. So a quadratic normally looks like this, but this went up 7. So now it is 1, 2, 3, 4, 5, 6, 7. It is right here. The vertex is at 7. So that means my range is the very bottom is at 7, and then it goes up to infinity. You can also say y is greater than or equal to 7. Everything is above 7, greater than or equal to 7. You could also put it in set notation. So you would put y such that y is greater than or equal to 7. These are the 3 different ways to write it. This is set notation, this is inequality notation, and this is interval notation. Interval, inequality, set. Write the linear equation that remains after you cancel the common base. Okay, so this is 2 to the power of 9 minus 4x equaling 1 over 4. Now, I can rewrite this as 1 over 2 squared, because 1 squared is 1, 2 squared is 4. So this is what it can look like now. Okay, now let me remind you of something. If you have 2 to the negative 2, you write this as 1 over 2 to the 2. If you have a negative exponent, you can make it positive by putting it into the denominator. So in this case, if I want to flip this 2, I need to make this negative. So this can be written as, this will stay the same. I can flip this 2 so that the exponent will now be negative. Okay, so now my base is matched. I have 2 to the power of something and 2 to the power of something. So you can just cancel out your bases and you set this part equal to each other. So you have 9 minus 4x equals negative 2. And that is this one. Which parent functions do not have a domain of all real numbers? A quadratic looks like this, and the domain is all real numbers, so that's not it. Absolute value looks like a V shape, and they go forever left, forever right. This is also all real numbers. An exponential graph, it goes forever to the left, and it goes this way, forever to the right. So this is also all real numbers. So those can't be it. Logarithmic, it has an asymptote along the y-axis, and from there, it goes to the right. So it never goes this way. So this one is not all real numbers. The square root graph, it starts at the origin and goes to the right. So it never goes this way. So this one's not all real numbers either. This one is 0 to infinity. This one is parentheses 0 to infinity because you can't be on the asymptote. Linear, this graph looks like this. It goes forever left and forever right. So this one's all real numbers. So that's not it. Cubic, that looks like this. So it goes forever left, forever right. So it's not cubic. So the only ones that do not have a domain of all real numbers, given these, were logarithmic, which is this graph, and square root, which is this graph. All the other ones listed here have a domain of all real numbers. Find the exact solution to e to the 2x plus 6 equals 27. First, we're going to subtract 6 from both sides. So you're left with e to the 2x equals 21. Now, to get rid of this e, I'm going to take the natural log of both sides so that those cancel out. I am left with 2x equals the natural log of 21. Now, all you do is divide by 2. So I'm going to type this into my calculator. Natural log of 21 divided by 2 is 1.52226. So that is the exact solution for this equation. Give the end behavior. So the highest degree is a 5, which is odd. Odd exponents will always look like this. If it's even, it will always look like this. okay? For even functions, the end behavior will always match. For odd functions, they will go separate ways. So this will look something like this graph, since it's odd. The end behaviors are opposite. And you can test that with Desmos. If you do x to the 3, it'll look like this. X to the 5, it'll look like this. X to the 7, and so on, it'll look like this. But if they're even, they'll look like that. So the end behavior. The end behavior, since it looks like this, will be the limit as x goes to the left. As I go this way, the graph goes down. So as the x values goes to the negative side, your function goes down to negative infinity. The limit as x goes to the right. As you move this way, your graph goes up. So that will be positive infinity. What are the intervals over which the graph is increasing and decreasing? Okay. So if you follow my pin, I'm going down from here to here, and it goes up, and then I'm going down again from here to here forever. Okay? So we're starting from on the left. Whenever you're talking about increasing and decreasing, you want to think about the domain where it's happening. So the domain from here to here is negative infinity to negative 2. And it's also decreasing from here to here. So the domain of that is 5 to, and it goes forever to the right, infinity. So this is where it is decreasing. Whenever you're asking for increasing and decreasing interval, you have to give me the domain where it's happening. Now, it is increasing from here to here. My pin is going up. So for increasing interval, the domain is from negative 2 to 5. That is where it is increasing. The table shows the temperature of a cup of water when it is placed in the freezer. What number is it approaching? So at 5 minutes, it's about 91 degrees. And as time goes on, it's getting colder and colder and colder. And the spaces between the numbers is getting smaller and smaller. It looks like it's approaching 32. And that makes sense because that's the temperature at which water freezes. What is the first step when solving the equation? Okay, well first, you're going to use the product property. Which means when you're adding logs and they have the same base, you can multiply them. So this is log base 3, and then you do x times this. So x times x minus 5. That's the first thing you would do, is combine it into one thing. So this is the first thing you would do. The second thing you would do is I would multiply this in. So this is log base 3 of x squared minus 5x equals log base 3 of 24. And then you can do the one-to-one property. Those match, so you can cancel them out. And you're just left with x squared minus 5x equals 24. And then from there, you would just solve it. It's a quadratic equation. But they just wanted the first step. So the first step is to combine them using the property of logs, the product property. Which of the following describes the discontinuities of this function? Whenever you have an asymptote, like right here, this line gets very close to it and this line gets very close to it. That is called an asymptote. Asymptotes are also called infinite discontinuities. Okay? They're also called infinite discontinuities. Okay? This right here is called a jump. A jump discontinuity is also called a non-removable discontinuity. So there is two types of discontinuities in this graph. Here is an infinite discontinuity, also known as an asymptote, and that is at the x value 0, and that's what it says right here. There's also a non-removable discontinuity, also known as a jump, right here at 3, x equals 3. So your answer here is C. So a removable discontinuity is a hole. So if there was a hole in the middle of the line, that is called a removable discontinuity, which we don't have here, okay? What type of discontinuity exists at f of -5? So -5 is 1, 2, 3, 4, right here is where -5 is. And it looks like there's an asymptote here. This part of the line gets very close to my asymptote, and so does this part of the line. So that is called an infinite discontinuity. What type of discontinuity exists at f of 3? 1, 2, 3, this is f of 3 right here. And it looks like that is a jump discontinuity. It goes from here to there. So that is a jump discontinuity, which is also known as non-removable. So that is A. What type of discontinuity exists at f of -8? 1, 2, 3, 4, 5, 6, 7, 8. This is -8 right here, and that is a hole, which is also called a removable discontinuity. Remember, a hole is also called a removable discontinuity. Give the discontinuities for x squared minus 5x minus 24 over x squared plus x minus 6. So you guys are going to have Desmos, so I'm going to go to Desmos. So I typed my equation from the problem, and this is the graph, and it looks like there is an infinite discontinuity right here. There's an asymptote right here. So remember, asymptotes are also called infinite discontinuities. Infinite discontinuity. So that's the only thing that this graph has, an infinite discontinuity. You have 250 coins in a game. So that is what you're starting off with, and you use up half of your coins in one day. What is the equation? So this sounds like an exponential decay equation, where A is your initial value and B is your rate. So in this case, you started out with 250 coins, and your rate, you used up to half of your coins in one day. So you were decaying by a half. So this is your equation.